Well, why did I do this FYP? I thought 7 years as an undergrad here is more than enough. And plus, I already had the chance to do some really cool mechanical engineering with Monash Motorsport and through the internships that gave me the chance to do here and abroad. And so, for my FYP, why not do something new? Machine learning is a field that has incredible implications for society, for the better or worse, and working on the responsible implementation of these technologies is really exciting to me. And plus, I've definitely learned some useful skills along the way. So I reached out to a few supervisors at Monash University talking about project ideas in this field, and I got that email from Klaus early on in the year. And they say the rest is history. Now, having this project in mind, it was time to start researching solutions. I found that since the late 2000s, advances in parallel computing has ushered in this golden age of artificial intelligence, and that has led to some really cool breakthroughs in the fields of computer vision as well as natural language processing, among others. But all these awesome applications boil down to a very simple concept, the neural network, which is made up of nodes. And these nodes learn to recognize combinations of inputs. It's not black magic, it's just the input as a matrix multiplied with a weight matrix associated with each node to get your output. These outputs are then fed into nodes a layer deeper, and so on, and so on. And then you get to your output and you find the difference between that and what you expect. And you'll find that this is a differentiable term, the product of a series of matrix multiplications, which makes finding the optimum weights literally just an extension on high school maths. The next big concept on top of that is a convolutional neural network, where you apply your matrix transformation to only one section of the image at a time. Now, the benefit of that is it doesn't matter how big your image is, you can see whether there is a line somewhere localized, if the line is a combination of features you're trying to detect. And then the next layer can then look at that and say, is there a combination of a few different lines that's interesting to make maybe a triangle? And then the layer on top of that will be able to say, all right, there's a triangle here. There's also two circles. What could that be? Maybe it's a bike. And so, naturally, you can say that how it might be useful for detecting features in images. So, for a classification network, for example, but we can also use it to do what we want, which is to make satellite images better. So, by saying that there is a bicycle somewhere in this image and taking sort of a low resolution image of that, your network can be able to say, all right, this is a bicycle, this is what's supposed to look like, let's make it a little bit better. So we want to do better. We want to make an image that can fool you into thinking it's real. Now, a smart undergrad had the same idea and decided to take this metaphor very literally. He applied an image classification network to the output of our network. And he called this network the discriminator. And all it does is classify the image as either real or fake. Now, the original network that we refer to as the generator has to lift its game to fool the discriminator. And during training, these better outputs in turn make the discriminator work harder. The adversarial action of these two networks makes the discriminator better at making something that seems photorealistic. Like this example, where the generator learns to turn a random input into something that can eventually pass as a handwritten digit. Well, did everything work the first time? No, it didn't. Generative adversarial networks are difficult to train because if your discriminator gets too good too quickly, everything the generator makes will be bad, and you don't get that virtuous feedback cycle. But despite the setbacks we had, the super resolution images, we used that as an input into a classification network that I was training for a competition in one of my units in first semester. And I won. So it shows that the additional detail that you can put into your image with an ESRGAN type network could actually make it work better. As we started to get into implementing it, I found a Pareto principle where 80% of work is responsible for 20% of the output really held water. Because I spent so much time in brain sweat working with Linux, getting the drivers to work, getting virtual environments to work, only to finally spend another whole lot of time getting paths and file names and working with that to work in Python. And finally, coming from a non-object oriented programming background, I had to get an idea of how to work with these deep learning frameworks like PyTorch. And finally, we can get down to the fun stuff, working with models, designing models, testing models, and getting stuck into the math behind it all as well, and the theory of how it all works. Now we're ready to put this all together. We get our low resolution data set, which comes from the European Space Agency Sentinel-2 satellite. And it has a wide field of view, also known as SWAVE. And that means while it's low res, it can cover the same geographical locations quite frequently. We also have our high resolution data set, this time coming from Digital Globe, a private company. Their satellites include WorldView 2. This dataset has a narrow swathe and isn't freely available across time like the Sentinel-2 data is. Now, what this means is that hopefully we can make our low-res data look like high-res data by applying our network. So we took these datasets and our network architecture and we trained it for a couple of days on a NVIDIA P100 GPU provided by the massive/M3 cluster at Monash University. And so before I get into the results, I like to extend my gratitude towards my wonderful supervisors who have helped me immensely in this project, the open source software community, Monash University, the European Space Agency, and did I forget anyone? Oh, of course, Stack Overflow. Well, let's have a look at our results. It looks great, right? Our output image seems to have restored a whole lot of the detail that's missing from the Sentinel-2 image that's present in the ground truth image. We also see a significant improvement in peak signal to noise ratio. But is it useful? In order to find out, I trained a second network to recognize buildings in images as a simulation of something that a real researcher might do. And as you can see here, my images show a dramatic improvement over the stock Sentinel-2 images when fed into this model in order to recognize the buildings. It's even found buildings that the original map missed. Crunching the numbers on its building detection algorithm, we see a quantifiable 3 times improvement on building detection. And that's it. Thank you for coming and watching my presentation. I hope it was informative. And I'll be happy to answer any questions or provide a demonstration of my model after this.